Theory of Relativity. Formulated by Albert Einstein in the first half of the 20th century, the theory of relativity was born in a fascinating context. Newtonian physics, well established for over 2 centuries, was faltering in the face of new findings indicating that classical laws were insufficient to describe large-scale phenomena, not to mention certain properties of light and electromagnetism. As a young man in his early 20s, Einstein ventured into uncharted realms, publishing his special theory of relativity in 1905 and later, in 1915, the general theory of relativity, thereby revolutionizing our understanding of space, time, and gravity. To grasp the magnitude of this shift, it's worth recalling that Isaac Newton's physics saw space and time as absolute backdrops. One could measure distances and durations without worrying about the observer's motion, given the idea of a universal time that would correct any differences. Einstein, however, argued that neither space nor time is universal, but rather dependent on the observer's state of motion. Under special relativity, the speed of light remains constant regardless of the frame of reference, meaning that an observer moving relative to another will measure distances and times differently. This leads to remarkable phenomena. Time dilation, a rapidly moving clock runs slower compared to a stationary one, and length contraction, objects traveling at high speed become compressed in the direction of travel. Although it might sound purely theoretical, numerous experiments and practical applications have confirmed these effects. Later, Einstein took a major leap forward with his general theory of relativity, which redefined gravity. According to his proposal, mass, or energy, warps the fabric of space-time, and that curvature determines the motion of bodies. It ceased to be a force that pulls, Newton-style, and instead became a geometry that dictates the paths of planets, stars, and even light itself. Thus, extremely massive objects, such as neutron stars or black holes, intensely distort space-time. Light bends when passing nearby, and the perception of time also changes. Consequently, gravity is no longer a simple, constant universal force, but rather a consequence of how the universe is woven. One emblematic example that confirmed this viewpoint came with the 1919 solar eclipse observation. Astronomers led by Arthur Eddington measured how the light from distant stars deflected slightly as it passed near the Sun, just as Einstein's theory predicted. This empirical validation not only led to general relativity's acceptance, but also launched Einstein to international fame, since his theory explained phenomena that traditional physics had not addressed. Perhaps the most direct and familiar practical consequence is seen in GPS usage. These satellites, orbiting Earth at high velocity and situated at altitudes where gravitational intensity differs from that at the surface, experience time at a distinct pace relative to our clocks down on Earth. Without relativistic corrections, both special and general, in the system, positional readings would be off by several meters each day. Thus, almost unnoticed, every time we consult GPS directions, we're relying on relativity implemented in algorithms that adjust for time differentials between satellites and our local reference. Another fascinating point is the light speed limit that special relativity imposes as an insurmountable barrier for any object with mass. Beyond its theoretical significance, this indicates a very real constraint on dreams of interstellar travel, forcing alternative thinking if we wish to reach other stars. Likewise, the existence of black holes, predicted by general relativity, remained for decades a theoretical curiosity until increasing evidence confirmed their effects. Nowadays, capturing images of black hole event horizons via synchronized radio telescopes has validated a central aspect of Einstein's theory in extreme conditions. On a philosophical plane, relativity also changed our understanding of reality. Space stopped being a fixed stage where events occur, and time ceased to be a universal, impartial flow. Instead, both merge into a space-time continuum in which simultaneity depends on one's frame of reference. This injects a sense of relativity that doesn't stop at physics but is often extended, perhaps oversimplifyingly, into culture and thinking, the idea that perspective influences the data we perceive. Even if Einstein never intended to apply his theory to moral or social fields, the popularizing of terms like everything is relative draws partly on misinterpretations of his work. Still, the seed of rethinking obvious concepts took root. Thus, the theory of relativity is far more than an academic curiosity. Its revised concepts of time and space affect everyday technology, spark investigations into the universe's beginning and end, and challenge our notions of how we see and measure reality. Einstein didn't just revolutionize physics, he introduced a new way of thinking, reminding us that what we take for granted, the uniform passing of time, the solidity of space, may be far more flexible and dynamic than our intuition suggests. Within that flexibility lies the wonder of realizing that we inhabit a cosmos far richer and stranger than we once dared to imagine. The double helix of DNA. The discovery of the structure of deoxyribonucleic acid, DNA, stands as one of the most influential milestones in modern biology. In the early 1950s, a group of researchers, including James Watson, Francis Crick, Rosalind Franklin, and Maurice Wilkins, worked in different labs but shared the common goal of unraveling the shape of the molecule that carries genetic information. Despite coming from somewhat varied backgrounds and interests, their efforts converged in publishing the famous double helix. A key piece of the puzzle lay in the so-called photograph 51, an image obtained via X-ray diffraction by Rosalind Franklin and her student. That pattern, which resembled a diffuse cross, hinted at the existence of a helical axis within the molecule. James Watson had access to these data and, together with Francis Crick, used them to build their double helix model. Two strands coiled around each other, joined by pairs of nitrogenous bases, adenine with thymine, guanine with cytosine. Beyond the elegance of this solution, it clarified how hereditary data are stored and duplicated. Why was this so revolutionary? Because inheritance, once a somewhat intangible mystery about how traits are passed from one generation to the next, became explainable in physical and chemical terms. DNA, with its arrangement of those bases, acts as a book of instructions that, when read, guides the synthesis of proteins, carrying all the implications for an organism's development and functioning. Immediately, it became clear that decoding the sequence of those bases allowed us to understand genetic variation, disease predispositions, and the evolution of species. This initial revolution paved the way for subsequent progress in gene sequencing, for example Sanger methods, which opened the door to the Human Genome Project in the 1990s. With that trove of information, biotechnology has managed to design gene therapies, modify cells to produce valuable substances like insulin, sequence pathogens to develop vaccines, and study the genetic diversity of countless organisms. Personalized medicine today thrives on identifying specific mutations so as to offer treatments adapted to each patient's biological profile. Nonetheless, the historical process wasn't without controversy. Rosalind Franklin, an expert in X-ray crystallography, proved vital in capturing and interpreting photograph 51, but for a long time she received less credit than many feel she deserved. James Watson and Francis Crick used some of Franklin's findings, compiled with Wilkins, to assemble their model. When the Nobel Prize arrived in 1962, it was awarded solely to Watson, Crick, and Wilkins, as Rosalind Franklin had died a few years prior, and the Nobel Prize is not awarded posthumously. This incident fueled debates on the role of women in science and the lack of recognition for their work. DNA, represented by those four letters, A, T, G, and C, thus emerges as the fundamental language of life as we know it. Discovering its double helix structure transformed biology from something largely descriptive into a molecular, explanatory field, merging chemistry and physics with life processes. Public imagination filled with both hopes and fears, curing genetic diseases, engineering organisms, raising ethical questions about embryo manipulation or trait selection. Now, in an age of gene editing with tools like CRISPR, the double helix remains at the core of these developments, allowing us to grasp the mechanisms that once were just glimpses of a mysterious code. Beyond the scientific achievements, the story of DNA underscores the value of collaboration and data sharing, as well as the urgency of recognizing everyone's contributions. One of its charms is that beneath the academic rigor lies a human narrative, the desire to decipher life's primary book, and the dream of unlocking new possibilities for health and knowledge. Thus, that double helix has become a symbol of contemporary biology and the immense potential held within each cell. The discovery of penicillin. In 1928, upon returning from his vacation, Scottish bacteriologist Alexander Fleming made a keen observation that would alter medical history. On one of his petri dishes, a mold, identified as Penicillium notatum, was preventing the growth of surrounding bacteria. Initially, this might have been dismissed as an annoying contamination, an unclean culture that should have been thrown away. Yet Fleming noticed something different. The clear halo around the mold hinted at a potent antibacterial effect. He deduced that this mold produced a substance capable of inhibiting bacterial proliferation. He called it penicillin, giving birth to what would become one of the most transformative discoveries in medicine. Fleming's immediate attempts to purify penicillin met with limited success. Although he published his observations, the scientific community paid relatively little attention. He lacked the means to convert this substance into a stable therapeutic agent, and there wasn't yet a well-established approach for mass-producing it. Nonetheless, the crucial seed was planted. In the following decade, other researchers would pick up that seed and cultivate it into a life-saving treatment. It was in the early 1940s that Australian pharmacologist Howard Florey, along with Ernst Chain and their colleagues at the University of Oxford, refined techniques to isolate and produce penicillin in greater quantities. They were motivated by the rising tide of wartime infections, especially on the front lines of World War II, where even minor wounds could lead to deadly bacterial infections like sepsis or gangrene. Laboratory trials on mice showed penicillin's dramatic efficacy. Infected rodents that received penicillin survived, while those untreated succumbed to infection. Impressed and spurred by these results, Florey and Chain took steps to bring penicillin into clinical use. Yet scaling up production was no trivial matter. The Oxford group had to rely on help from American drug companies, who, with the impetus of the war effort, facilitated large-scale fermentation processes. Old factories were repurposed to grow vast quantities of penicillium, and biochemical refinements were developed to extract the active ingredient. By 1943 to 1944, penicillin was already being tested and used on injured soldiers, significantly reducing mortality on battlefields in Europe and the Pacific. After the war, as mass production improved, penicillin became accessible for civilian use, treating illnesses that had previously been life-threatening, like pneumonia, scarlet fever, and more. Such sweeping success wasn't merely a triumph of science, it was also a social revolution in healthcare. Rates of fatal infections declined sharply in hospitals. Surgical procedures could take greater risks, knowing that secondary infections were less likely to kill the patient, and the post-operative survival improved. The hype around penicillin spurred further exploration. Soon, entire families of antibiotics were discovered: streptomycin, tetracyclines, and sulfonamides, to name just a few. These, in combination, sparked the antibiotic era, where for the first time in human history, bacterial infections lost much of their lethal power in many parts of the world. Yet, what might be called a miracle drug also introduced new challenges: overuse, misuse, and the prescription of antibiotics in unwarranted situations accelerated the evolution of resistant bacterial strains. Fleming himself, upon receiving the Nobel Prize in 1945, together with Florey and Chain, warned of the possibility that bacteria could develop resistance if the antibiotic was not used prudently. His cautionary words went largely unheeded for decades, and by the late 20th century, antibiotic-resistant pathogens began to appear worldwide. Now we face so-called superbugs, and public health experts keep reminding us that we risk entering a post-antibiotic era if novel drugs aren't discovered and antibiotic stewardship isn't practiced carefully. Despite these problems, the importance of penicillin remains profound. It stands as a testament to how serendipity and careful scientific observation can reshape the entire landscape of medicine. A seemingly forgettable petri dish with an odd mold blossomed into a cure for infections once deemed incurable. It saved countless soldiers in World War II, drastically cut maternal and child mortality in peacetime, and led to a fundamental shift in public health strategy around the globe. It also illustrated that major leaps in science can come from paying attention to anomalies. Fleming might have simply tossed out that moldy dish had his curiosity not made him think, "Why aren't bacteria growing here?" That moment of insight opened an avenue that labs around the world raced to explore. The environment in which Fleming worked, St. Mary's Hospital in London, wasn't even specialized in antibiotic research at the time, yet the discovery put it on the map. In subsequent years, pharmaceutical companies took up the mantle, industrializing antibiotic production. Meanwhile, allied scientific inquiries fleshed out the biochemical intricacies behind penicillin, explaining how it breaks down bacterial cell walls and clarifying why certain microbes can evolve ways to withstand it. Each step along the antibiotic pipeline, research, development, clinical trials, distribution, became a model for how science and industry could cooperate under pressing needs. Today, penicillin's story acts both as a caution and an inspiration. On one hand, the rising tide of antimicrobial resistance warns us that no discovery remains foolproof forever. Nature adapts. On the other hand, it reminds us that even small, accidental observations can initiate extraordinary progress. Nearly a century after Fleming's happy accident, the search for new antibiotics and the improvement of existing ones continue, often in the shadow of superbugs that push us to innovate. Ultimately, the discovery of penicillin epitomizes the dual nature of breakthroughs. An unexpected observation can spark a medical revolution, freeing society from once fatal scourges, but each success also places upon us the responsibility to preserve that achievement. Antibiotics transformed surgery, battlefield medicine, and everyday bacterial infection treatments, and remain a cornerstone of modern healthcare. For all the challenges that resistance poses, penicillin's journey from a moldy plate to a global lifesaver stands as one of the great narratives in scientific history, a narrative that, in its unfolding, underscores how vigilance, curiosity, and caution go hand in hand when pushing the boundaries of human knowledge. The Big Bang and the expansion of the universe, and at the start of the 20th century, most astronomers pictured a stable, unchanging universe. However, the work of Vesto Slipher, and more notably Edwin Hubble, began to reshape that understanding. In the 1920s, while studying the light from different galaxies, Hubble found that nearly all of them showed a redshift, meaning they were receding from us. Moreover, the farther away a galaxy was, the faster it was receding. This relationship, known as Hubble's law, pointed to the idea of a universe in expansion instead of a static stage with a random scatter of objects. Extrapolating backward in time, the cosmos had to have been much smaller and denser in the past. This expanding universe concept was disruptive. Many scientists and thinkers had believed that everything existed in a more or less constant state from the beginning of time. But if galaxies are moving away from each other, it's logical to imagine that long ago, all matter was packed much closer together. The Belgian priest and physicist Georges Lemaitre, for instance, proposed that the universe had originated from a primeval atom, or something akin to it, laying the groundwork for what would become the Big Bang model. Early on, the theory faced skepticism and even ridicule. Some called it the Big Bang mockingly, but observational data gradually piled up in its favor. The defining confirmation emerged in the 1960s with the discovery of the cosmic microwave background, CMB. Two Bell Labs engineers, Arno Penzias and Robert Wilson, were calibrating a microwave antenna for telecommunication experiments when they detected a background noise seemingly coming from every direction in the sky with the same intensity. At first, they blamed interference or instrument contamination, perhaps pigeon droppings. But once those possibilities were ruled out, they concluded that they were measuring the remnant radiation of a universe once much hotter and denser, a fossil echo of that great explosion. This nearly uniform radiation, visible from all directions, is interpreted as the light released when the universe was about 380,000 years old, having cooled enough for matter and radiation to separate. It became a powerful piece of evidence for a cosmological model positing a hot, dense beginning. From this discovery, the Big Bang model became the standard explanation for the cosmos's evolution. The universe, according to this outlook, began around 13.8 billion years ago in a state of extraordinary density and temperature, and has expanded and cooled ever since. Hydrogen and helium formed in those first minutes, while heavier elements like carbon and oxygen arose later inside stars, then scattered with supernova explosions. Consequently, the chemistry of our bodies, the composition of planets, and the variety of substances known to us all hinge on a protracted cosmic history. We don't merely exist on a cosmic stage, we're the result of a process that started with that primeval blaze. The expansion is described by mathematical models based on Einstein's general relativity. Those equations help explain, for instance, how the expansion rate changes over time and how the universe's geometry, open, closed, or flat, influences its fate. Recent observations indicate a mysterious force known as dark energy is accelerating that expansion, adding yet more intrigue. It's not just that galaxies recede from each other, but they do so at an ever-increasing speed. This gives rise to various scenarios, perhaps an indefinitely continuing expansion, leading to a cold, empty cosmos, or alternative outcomes not fully understood. We lack certainty about which future will unfold, which doesn't signal defeat, but instead highlights the perpetual need for cosmic inquiry. For humankind, living in a universe with a beginning and potentially an end shattered old notions of an eternal static reality. On the one hand, there is humility in grasping that our galaxy is just one among billions, and everything traces back to a singular primordial state. On the other hand, it triggers curiosity about how life emerged amid such an expanding universe, whether it might exist elsewhere or if it's in fact ubiquitous. The Big Bang is no longer a remote hypothesis. It's now deeply entrenched in popular culture, discussed in classrooms and casual conversations, and even referenced in comedic television, as hinted by a famous sitcom title. On a daily basis, we don't perceive this expansion because local forces, gravitational, electromagnetic, keep objects bound. But on intergalactic scales, the effect dominates. Each day, observations sharpen via space telescopes like Hubble, Spitzer, or the newer James Webb, which probe ever deeper into cosmic history, giving us windows into the past. Witnessing light from galaxies that existed when the universe was just a fraction of its current age is akin to glimpsing cosmic childhood. The existential aspect of these ideas is the realization that we live in a dynamic universe with a billion-year history, and that our species is a recent newcomer on the cosmic stage. Plus, its ultimate outcome isn't fully known. Maybe it will keep spreading out forever, drifting into a cold, lonely horizon, or perhaps other, still mysterious factors will arise. Far from being discouraging, this uncertainty inspires us to appreciate human creativity as we explore the skies. With every fresh discovery, we confirm how much remains unknown about dark matter, dark energy, and the deeper structure of space-time. In sum, the Big Bang Theory and the universe's expansion rest on pillars like Hubble's law, the recession of galaxies at speeds proportional to distance, and the detection of the cosmic microwave background. These cornerstones let us outline a grand cosmic narrative. From a compressed, heated state emerged an immense realm populated by stars and galaxies that disperse as time passes. We, in our small corner, find ourselves in the midst of that evolution, striving to comprehend it and locate our place within. Recognizing that the universe has a past and a future dissolves the notion of any static, eternal present, spurring us to envision what role we might play in this unending story. Quantum physics. In the early 20th century, quantum physics ushered in a profound revolution in how we conceive of matter, energy, and ultimately, reality. Until then, Newtonian physics and Maxwell's electromagnetism seemed sufficient to describe nature. But certain experiments involving light and heat, among them the black-body radiation problem, started revealing that established laws didn't adequately address phenomena at very small scales or at high energies. It was Max Planck who, in 1900, opened an unsuspected path by proposing that energy is emitted or absorbed in discrete quantities, which he called quanta. That paradigm shift, initially viewed as a mathematical expedient for solving an experimental impasse, would eventually pave the way for quantum mechanics. Soon afterward, other scientists joined this new direction. Albert Einstein, for instance, used the idea of light quanta, photons, to explain the photoelectric effect, later receiving the Nobel Prize for that, not for relativity, as many believe. Then came Niels Bohr, Werner Heisenberg, and Erwin Schrödinger, among others, who laid the foundations of what we now call quantum physics or quantum mechanics. Their contributions rattled the core of our intuition. Subatomic particles like electrons could sometimes behave like waves, sometimes like particles, and the very act of measurement altered what was being measured. Perhaps one of the most surprising concepts is wave-particle duality. In classical physics, something was either a wave, like sound, which propagates diffusely, or a particle, a mass-bearing object localizable in space. Yet at the quantum level, that distinction dissolves. The same entity can show wave properties in one experiment, while in another it acts like a point-like particle. The famous double slit experiment, for example, demonstrates how electrons produce interference patterns typical of waves, even though, on detection, each electron is recorded as an individual particle impact. Heisenberg's uncertainty principle added another dimension, positing that we can't simultaneously know both the exact position and the momentum or velocity of a particle. If we measure position with great accuracy, the momentum reading becomes more imprecise, and vice versa. This isn't about the limits of our instruments, but rather about the nature of quantum reality itself. The theoretical restriction radically undermined the dream of measuring everything with infinite precision, revealing inescapable boundaries in our knowledge of the subatomic world. The repercussions go far beyond abstract speculation. Our electronic devices, like transistors and diodes, are built on quantum principles. The laser, now found in barcode scanners, medical instruments, and telecommunications, relies on Einstein's concept of stimulated emission, in which electrons move between energy levels to generate a coherent beam of light. Without quantum physics, electronics wouldn't have progressed as quickly, and we might still live in a world without computer chips or portable devices. In truth, practically every gadget we turn on has, in its origins, the stamp of quantum mechanics. However, the most provocative aspect of quantum mechanics might be its philosophical draw. Schrödinger's cat, proposed by Erwin Schrödinger in 1935, is a thought experiment that confronts our ideas of reality with quantum superposition. In the idealized setup, a cat is locked in a box with a device tied to a radioactive decay process, which, if triggered, would release poison and kill the animal. As long as no one opens the box to observe, the quantum system deems the cat to be both alive and dead at once, in a state of superposition. Once we measure, by opening the box, that superposition collapses into one of the two states. This scenario underscores the dissonance between quantum physics and our everyday notion of reality, as we can't fathom a cat being alive and dead simultaneously. Yet, according to quantum interpretation, things aren't so simple. The observer's role is integral to defining the state. Another intriguing facet is quantum entanglement, in which two particles remain correlated such that what happens to one seems to affect the other instantaneously, no matter how distant they are. Einstein dubbed this spooky action at a distance, expressing his unease, though experiments in particle physics ultimately confirmed that these correlations are real. This points to features of nature transcending our ordinary ideas of local causality. Nowadays, quantum physics doesn't just account for the microscopic realm, it also inspires futuristic fields. Quantum computing and quantum communication promise extraordinary achievements in data encryption and processing. There's also ongoing research into merging quantum mechanics with relativity in pursuit of a quantum theory of gravity that might explain, for instance, black holes at a fundamental level, an undertaking that would rank among the greatest feats in scientific history. In day-to-day life, most people don't ask whether their phone or laser printer works thanks to quantum mechanics. Yet in fact, quantum mechanics, despite its apparent strangeness, underlies all modern electronics and telecommunications. Hence, a domain born from seemingly modest experiments and puzzling paradoxes ended up redefining technological horizons. Meanwhile, it left open questions. Is reality probabilistic? What determines the crossover from the quantum realm to the classical? Ultimately, to what extent can we embrace the idea that, at the smallest scales, the universe operates by rules quite foreign to everyday experience? Quantum physics reminds us that not everything fits neatly into certainty. There are levels of nature where the rules sharply diverge from what we call common sense. This tension between what we measure and how we interpret those measurements offers an endless space for exploration and invention, shaping much of the technological society we inhabit. The Copernican revolution and heliocentrism. For centuries, the notion that Earth lay at the center of the universe reigned largely unchallenged. Denying this idea in medieval and Renaissance Europe meant clashing with the official doctrine that had its roots in ancient Greece and was refined by Christian scholasticism. Claudius Ptolemy's 2nd century geocentric model, fully integrated into ecclesiastical theology and cosmology, not only defined astronomy but also fit with the belief in a God-ordained universe in which humankind and its planet were at center stage. Within that setting, Nicholas Copernicus, 1473 to 1543, introduced a radical hypothesis that the Sun, not the Earth, lay at the heart of the system. In his work, De Revolutionibus Orbium Coelestium, published shortly before his death, he argued that the planets, including Earth, revolved around the Sun on circular orbits, with certain corrections. This idea wasn't a spontaneous creation. Similar theories had arisen in ancient Greece, e.g. Aristarchus of Samos. But Copernicus supplied the mathematical underpinnings and molded a theory coherent enough to challenge the orthodoxy of the time. The shift wasn't immediate or simple. Decades passed before it took firm hold in the astronomical community and the broader culture. Not until other scientists and observers contributed direct evidence did heliocentrism gain strong momentum. Johannes Kepler, after examining Tycho Brahe's meticulous data, substituted the circular orbits of Copernicus with elliptical ones. Galileo Galilei, with his telescope, observed satellites orbiting Jupiter, proving not everything revolved around Earth, and phases of Venus consistent with Copernicus's model. Later, Isaac Newton, with his universal law of gravitation, presented the unifying explanation of why those movements happened as they did. Collectively, these contributions ignited what we now consider modern astronomy. To appreciate the importance of this paradigm shift, it's useful to place it within the worldview of that era. Until then, Earth was believed to be the motionless, privileged point at the center, with the sun, moon, and planets circling around in crystalline spheres. Faith and Aristotelian philosophy had merged to uphold a closed, stable image of the cosmos. By declaring, "No, the Earth is the one moving," Copernicus didn't just alter astronomy but also the symbolic relationship between humankind and the cosmos. Earth's demotion from that central throne made us just one more planet in orbit, alongside others. That blow to anthropocentrism was among the first major steps in dismantling the notion that everything revolved around us. Consequently, cultural conflict arose on a grand scale. Religious authorities responded warily, at times with hostility. The most famous episode involved Galileo, compelled to renounce his convictions before the Roman Inquisition, culminating in the likely legendary "Eppur si muove," and yet it moves, which symbolizes science's resilience in the face of censorship. Even though the reception of heliocentrism was not as stark as a total clash between science and the church, there were middle ground stances and alliances. The popular narrative of Galileo battling ecclesiastical power became a foundational myth for modern science. From the heliocentric breakthrough, astronomy grew ever more sophisticated, probing the movements of planets, the nature of celestial bodies, and later on, building toward Newton's laws, which encompassed both celestial mechanics and terrestrial objects in a single framework. The legacy of the Copernican revolution transcended solving how the heavens move. It reshaped scientific methodology, promoting empirical observation and mathematical validation over tradition. That same spirit would, centuries later, fuel Einsteinian physics, the Big Bang cosmology, and much of what we now term scientific thought. Symbolically, accepting that we're just another planet dispelled the notion of a universe designed exclusively for humankind. Ultimately, the realization that our star is merely one of countless in a galaxy teeming with hundreds of billions of suns, and that such galaxies number beyond measure, reduced Earth to a modest cosmic corner. The first main leap toward that decentralization of humanity was indeed Copernican heliocentrism, a bold intellectual act that cemented modern astronomy and our contemporary cosmic vision. That revolution didn't end with Copernicus, Galileo, or Kepler. They merely lit the fuse. Science history would continue nurturing this seed, enabling the systematic exploration of the skies and the future dispatch of spacecraft across the solar system. But most significant is that, thanks to this conceptual pivot, human thought learned not to trust appearances too quickly, relying instead on rigorous observation and calculation to describe reality. From that moment on, the boldness of putting the sun at the center stands as a reminder that empirical evidence can overturn centuries of conviction, ushering in a mindset that's open to revision. The Pareto principle, 80-20 rule. The Pareto principle, also called the 80-20 rule, puts forth an apparently simple idea. In many areas of life, roughly 80% of outcomes stem from merely 20% of the causes. This concept is attributed to the Italian economist Vilfredo Pareto, who, at the end of the 19th century, noticed that wealth distribution in his country was highly skewed. A small fraction of the population, the 20%, owned most of the resources, close to 80%. Over time, people identified this ratio in countless other settings. In sales, a 20% slice of clients can account for the lion's share of revenue. In time management, a handful of crucial tasks might yield most of the progress. What makes the 80-20 rule appealing is its approximate yet broadly recognizable universality. It doesn't always apply with strict mathematical precision, but the notion of imbalance frequently emerges. We might realize, for instance, that we wear only 20% of the clothes in our closet most of the time, or that in a business, a few products bring in the majority of total profits. Recognizing this pattern means understanding that not all things cost the same or generate the same returns. Focusing on that small pivotal fraction produces much greater benefits than distributing efforts evenly. How does this principle translate into everyday life? First, it helps define priorities. If we need to achieve certain goals at work, identifying the 20% of activities that truly drive results, crucial client meetings, key proposal development, could save us from wasting time on secondary tasks. In personal life, it might mean finding those minimal habits, perhaps a balanced diet, enough rest, and some exercise, that yield 80% of our daily well-being. The goal is to avoid scattering our energies by trying to tackle an endless list of minor issues with the same intensity as the major ones. Second, it lightens mental pressure to accomplish everything perfectly. Once we see that only a small set of actions deliver a large impact, the rest, while not useless, becomes secondary. We can handle it when time allows without feeling guilty for not treating it with the same urgency. This filter is hugely valuable. In an era crowded with information and demands, distinguishing what's essential from what's secondary becomes an act of liberation. In business, the 80-20 rule is evident. By analyzing sales, one might find that a certain 20% of clients generate the majority of income, or, in production, a small range of products accounts for most of the revenue. Strategy then focuses on nurturing those high-performance areas while optimizing everything else with less urgency. But well beyond a corporate context, the Pareto principle applies to any endeavor where this inequality in results can be detected. On a personal level, we might ask ourselves, which 20% of my habits bring me 80% of my emotional balance, health, or productivity? We may discover that simply getting enough sleep and planning our day a bit covers the majority of our needs, while other activities, though helpful, are less critical. This sort of reflection alleviates stress by showing us that we don't need to be stellar at 100% of our tasks if a small core of them suffices to meet the majority of our goals. Another interesting benefit appears in time management. The Pareto principle teaches that perhaps 20% of our schedule, used wisely, maybe a couple of well-planned hours, could provide the foundation for 80% of our achievements. The rest of the day might still be necessary for other duties, but knowing that a focused and optimized fraction of time can handle what's most vital offers a big sense of relief. It's quite different to feel, I can't do it all, versus, if I handle my 20% priorities, I'll cover most of what matters. Of course, this doesn't mean ignoring the remaining 80%. Those minor tasks can add quality to our day or be indispensable on a social or emotional level, even if they don't produce a high, measurable outcome. Pareto's principle doesn't intend to dismiss them. Rather, it highlights that from a standpoint of impact, the core often lies in a smaller subset. Thinking about this before bedtime can help us do a quick self-check. Did I take care of that crucial 20% in my day, the part that leads to 80% of what's important? If so, we can rest easy, not fretting over the myriad matters we didn't get to. In the morning, with a clear sense of priorities, it's easier to press on without constant distractions. Even when considering our personal relationships, we might see that most of our joy, that 80%, comes from a handful of key connections which we should value and nurture. In sum, the Pareto principle, or the 80-20 rule, isn't an absolute law, but rather an invitation to recognize how results are often distributed unequally. By directing our time and resources to what genuinely delivers value, we're freed from the mental load of trying to do everything equally well, and instead concentrate on that smaller share of efforts that determines the majority of our success. In this sense, it can be viewed as an approach to organization and prioritization, perfect for not getting lost in the noise and focusing on what truly makes a difference. Atomic structure and atomic models, the idea that matter is composed of atoms, traces back to ancient times, but for centuries it remained a mere philosophical conjecture. It wasn't until the 19th century that the British chemist John Dalton put forth a model backed by experimental evidence. He saw the atom as the indivisible unit of the elements, explaining that combinations of these building blocks produced compounds. Still, Dalton continued to picture atoms as small, solid spheres, indivisible and lacking internal structure. Only around the turn of the 20th century did research on electricity and radioactivity begin to challenge that supposed indivisibility. The physicist J.J. Thomson introduced in 1897 the discovery of the electron, a negatively charged particle far smaller than the atom. With that, he proposed the famous plum pudding, or raisin pudding, model. The atom would be a positive sphere in which electrons, like raisins, were distributed. This model explained some phenomena but soon proved insufficient. Ernest Rutherford's gold foil experiment, 1911, showed that positive charge was concentrated in a tiny nucleus, while most of the atom was empty space. Those alpha particles shot at the foil went straight through without deflection, except in rare instances implying a very small, massive nucleus with electrons orbiting around it. However, Rutherford's planetary-like model posed stability problems under classical physics. If electrons orbited like planets, they should radiate energy due to their acceleration and collapse into the nucleus. It was Niels Bohr, in 1913, who introduced quantized orbits, wherein the electron only occupied specific energy levels and didn't radiate while in them, thus preserving atomic stability. Even so, it soon became clear that orbits akin to little planets weren't enough to account for more complex spectra or detailed chemical behavior. Subsequent evolution connected to quantum mechanics, with contributions from Louis de Broglie, Erwin Schrödinger, Werner Heisenberg, among others, led to the notion of the atom as a nucleus containing protons and neutrons, surrounded by probability clouds where it's most likely to find electrons. In other words, gone was the plum pudding in favor of a central nucleus with electrons interacting in a far more complex environment. It was understood that electrons possessed the ability to exist in quantum states and that measuring position or momentum affected the result. These conceptual shifts weren't just fascinating in theory, they also had major implications for science and technology. Understanding the atomic nucleus opened the door to nuclear energy, whether through controlled fission in reactors to generate electricity or uncontrolled fission in atomic weapons with their devastating consequences. During the second half of the 20th century, scientists explored fusion, though practical commercial use remains a challenge. Meanwhile, the understanding of electronic structure led to deep insights in modern chemistry. The way electrons are arranged in layers and orbitals explains chemical bonding, reactions, and how compounds form. It also fueled the creation of new materials with targeted properties, semiconductors, advanced polymers, superconductors, etc. Far from being a simple, solid ball, the atom became a true, complex system with quantized interactions. Grasping that complexity translated into the ability to manipulate matter at unimaginable scales. From designing medicines, selecting molecules with precise electronic interactions, to creating ever smaller and more powerful electronic chips. Even in everyday life, the atom's concept influences everything. the way fuels burn, how batteries work, medical uses of radioactive isotopes, and the sensors that measure environmental radiation. Hence, the story of atomic models is a vivid tale of observations and rethinks, Dalton envisioning tiny, indivisible balls, Thomson discovering the electron and proposing the plum pudding, Rutherford revealing the nucleus and the atom's huge emptiness, Bohr adding discrete energy levels, quantum mechanics providing electronic orbitals, and probability. Each step overturned prior thinking and enriched our understanding, revealing that matter, which seems so solid, is mostly empty space, hosting a dance of particles governed by surprising principles. Today, the atomic model is essential for materials science, nanotechnology, nuclear medicine, pharmaceuticals, and an unending list of applications. It also signaled a cultural revolution, realizing that fundamental forces and atomic-level particles largely shape the visible world. Whenever we consider a sturdy metal or a transparent crystal, we're effectively talking about how electrons and nuclei are arranged on nanometric scales. Thus, the microscopic realm isn't just a footnote, but an active foundation for most of the phenomena defining our day-to-day reality. The theory of continental drift. In the early 20th century, the German meteorologist Alfred Wegener noticed how the coastlines on either side of the Atlantic Ocean, particularly South America and Africa, seemed to fit together like puzzle pieces, and he proposed a revolutionary concept. The continents weren't fixed, immovable landmasses, but had once been joined in a single supercontinent, which he called Pangaea, then gradually split apart over millions of years. This was the birth of the continental drift theory, positing that continents slowly shift across Earth's surface. At first, the scientific community reacted with great skepticism. Wegener lacked a clear mechanism explaining how such immense blocks of land could float or slip. Moreover, geology at the time generally presumed that the positions of continents and oceans were essentially permanent. Many geologists derided Wegener's idea, viewing it as merely a geometrical coincidence with insufficient proof. His notion of continental drift required several decades to gain real acceptance. The decisive turn came in the mid-20th century with the development of plate tectonics. Scientists gathered evidence from the ocean floors, measuring paleomagnetism, the orientation of magnetic minerals set according to Earth's polarity at the time seafloor crust formed, and detected the expansion of the seafloor. It was discovered that the lithosphere, the Earth's rigid outer layer, is divided into plates moving atop the hotter, more pliable asthenosphere. It soon became clear that at plate boundaries, where plates collide or separate, mountain ranges, faults, ocean trenches, and subduction zones form, fueling earthquakes and volcanoes. Thus Wegener's concept finally found its missing explanation. Continents travel because they ride on these continuously drifting tectonic plates. This paradigm shift not only unified geological knowledge, but also linked mountain formation, seismic events, and volcanic activity under a single global model. Once confirmed by plate tectonics, continental drift transformed geology from a static classification of rocks into a dynamic science capable of explaining Earth's history on a grand scale. Mountain belts, for example, can now be seen as byproducts of colliding plates. Volcanic island arcs are produced by hotspots or subduction zones along plate edges. Additionally, continental drift has enormous consequences for understanding the evolution of life and the distribution of species. When we wonder why identical fossils are found on continents now separated by oceans, or why Madagascar's wildlife is so distinctive, plate tectonics provides answers. In the past, these lands were connected, later drifting apart and interrupting migration routes, leading to independent processes of speciation. The evolutionary history of plants and animals was shaped by these breakups and collisions of landmasses. Thus, the fossil record holds patterns that only make sense when we accept a changing planet. Likewise, the tectonic model invites speculation about Earth's future. The continents haven't ceased moving. Today, the Americas and Africa continue drifting apart, while parts of the Pacific Ocean are shrinking in certain regions. In tens of millions of years, our planet's geography will be different again. Although these changes are slow compared to a human lifetime, recalling that the Earth's crust is not static, but rather flowing and regenerating underscores how far we've come from older ideas of a rigid, timeless world. In short, continental drift has evolved from a daring hypothesis into one of the cornerstones of modern geology. We can now explain mountain belts, continental displacement, the creation of ocean basins, and the interaction of tectonic plates in all their dynamism. Multiple fields interconnect here: paleontology, reconstructing life trajectories based on fossil distribution; geophysics, examining the planet's internal dynamics; and biogeography, locating species distribution according to which migrations were possible while continents were joined. The picture is that of a living Earth, with its continents moving at about the speed fingernails grow, yet over geologic eras, that small pace is enough to place entire oceans between lands that once formed a single, contiguous mass. The Theory of Evolution by Darwin. In 1859, Charles Darwin shook the foundations of biology by publishing On the Origin of Species, presenting his theory of evolution through natural selection. He started from the premise that, over many generations, populations of organisms undergo slight variations. Some of these variations prove advantageous in their environment, so individuals displaying them tend to survive and reproduce more successfully, passing those traits on. Over thousands or millions of years, these modifications accumulate, giving rise to new forms of life or such significant changes that the original species may transform or branch into distinct lineages. At the time, the notion that species weren't fixed contradicted the then common static view, which attributed organic diversity to separate acts of creation. By drawing on observations made during his travels, most famously in the Galapagos Islands, fossil collections, and exchanges with other naturalists, Darwin painted a radically different picture. Biodiversity results from successive modifications, selected through interactions with the environment. Hence the seeming perfection of certain features, like finch beaks adapted to specific food sources, ceased to appear as a pre-established design and came to be seen as the outcome of selection over countless generations. However, Darwin's theory wasn't a sealed package. His contemporaries criticized it for lacking a precise explanation of how these variations were inherited or blended in offspring. It was only later, with Mendelian genetics, rediscovered in the early 20th century, and the subsequent rise of the neo-Darwinian synthesis, that the concepts of genes and mutations as the basis of variation were integrated. This gave the idea of natural selection a more complete framework. Beneficial genes arising at random spread if they confer advantage, while less favorable ones tend to vanish. Thus, combining genetics and Darwin's proposition fortified evolutionary biology. The impact of this theory extended far beyond pure science. Until the 19th century, people generally believed every species had been created as is and remained unchanged. Darwin's ideas dismantled that static vision. Life became a process in continual flux, where species arise, change, or go extinct, and where their relationships can be traced as branches of a single tree of life. This was among the major blows to the notion of a fixed, unalterable order, much as heliocentrism had moved Earth from the center of the cosmos. It sparked philosophical reflections about humankind's place in nature and ignited religious and social controversies on a large scale. Today, evolutionary theory is deemed fundamental in biology, underpinning fields as varied as ecology, paleontology, population genetics, molecular biology, and even medicine, for instance in understanding antibiotic resistance or virus evolution. Even now, there are circles in which evolution triggers apprehension or debate, especially regarding philosophical or theological interpretations. Nonetheless, within the scientific community, the principle of evolution by natural selection, enhanced by molecular biology, epigenetics, and many other areas, remains the best explanation for life's diversity. Therefore, grasping Darwin's proposal and its subsequent extensions is not merely learning a scientific fact, but rather appreciating the history of how organisms connect over time. Through fossils and DNA sequences, we can uncover unexpected kinships. A land mammal and a whale may share distant ancestors, while the marsupial lineage in the Americas and Australia demonstrates parallel evolutionary processes on different parts of the globe. This interconnected view reshapes our notion of species and the universal family tree. Simultaneously, it prompts us to question our own role in this ever-evolving tapestry that is the biosphere. In short, Darwin's theory of evolution marks a watershed moment. It goes beyond explaining how species change. It provides a unifying framework for life on Earth, weaving the origin of each living being into a global phylogeny and laying the groundwork for understanding phenomena as diverse as embryonic development, drug resistance, or comparative anatomy. Its relevance endures in modern biology, and even subsequent discoveries that expand evolutionary explanations do not challenge the essential principle of change driven by variation and selection. They refine it. Thus, Darwin's legacy remains an ongoing field, inviting us to keep exploring the shared story of all living things.